Our next topic is something called Newton's law of gravity. And you might think we've already talked about gravity, but we're going to do it for astronomical objects rather than just for things near the surface of the Earth. The Moon is a natural satellite of the Earth and orbits in a nearly circular orbit with a radius of 3.84 times 10 to the 8 meters. Use our method where g provides the necessary centripetal acceleration to compute the period t in days for the Moon's orbit, remembering that one day is 86,400 seconds. So we're going to say, well, we're saying that v squared over r is being provided by g, so that v is the square root of gr, which is the square root of 9.8 meters per second squared times 3.84 times 10 to the 8 meters, which is something like 61,344 meters per second. And you might wonder, well, how does that help? Because we'll also say that v is the distance traveled over the time taken. So it's going to be 2 pi r over the thing we want. Or the period t is 2 pi r over v. So 2 pi times 3.84 times 10 to the 8 meters over 61,344 meters per second. Just about 39,331 seconds, which is about 0.45 days. So this says that the Moon orbit would take 0.45 days. But the Moon actually takes much longer than that. It takes 1 month to orbit the Earth. In fact, that's the origin of the word month in English. It's a month. It's about 28 days. So therefore, something's not right. That's the most important thing to recognize here. Something's gone wrong. What's gone wrong? The error comes from assuming that the acceleration of the Moon due to the Earth is still g, 9.8 meters per second square. That turns out not to be true. The nature of the force law that we actually have is crucial to understand the motion of planetary objects, and it consumed a lot of intellectual effort for centuries. But eventually, Isaac Newton, you might remember him, proposed a law of universal gravitation, which explained motions in the solar system and beyond. So one of Newton's things is he invented circular motion, not really the thing, but our understanding of it. He helped push forward our understanding of dynamics, and he did this calculation and basically said the Moon couldn't really be being pulled on the Earth at a rate of g. What he actually said is that he came up with a force law that says the Moon is still pulled on by the Earth the same way that something near the surface of the Earth, let's say an apple, is, but that the value of g is different. The law of universal gravitation says the force between two objects of mass m1 and 2 is given by their product of their masses, m1 times m2, divided by the square of the distance between them. So this distance shows up as a square, and that's going to be really important. All right. You might also have noticed there's this thing out front, this constant g. Big G is called the universal gravitational constant. It is truly universal. It has the same value everywhere in the universe at all times during the universe's history. Post-Newtonian theories of gravity kind of play with this condition, but we're going to take it as true. It's the same everywhere at all times. I'm going to defer talking about its precise value until later, but right now keep in mind that it's a relatively small number. Its purpose there is to convert the things that we have into newtons. All right, we have kilograms times kilograms over meter squared. We want the thing to be newtons. We need some sort of conversion factor that basically tells us how strong gravity is in our universe. This law is universal in that every object in the universe exerts a gravitational force on every other object. Strictly speaking, this law is only true for point objects. You need to use calculus if your object is not generally a sphere or a point, but that's okay because most things that we're going to talk about astronomically are in fact spheres, and the details are just details. They don't really change what goes on. F sub big G depends on the product of the masses, which guarantees that it automatically satisfies Newton's third law. It's the same on each object. This isn't surprising. If Newton had come up with a thing that didn't satisfy third law, he'd either not have published the third law or not have published the force. One of those would have to go away. Also, this force law establishes that mass is the charge for gravity. In other words, you get more gravity when you have more mass. Why gravitation should depend on inertia is unanswered in Newton's laws. It took until about 1915 in Einstein to come up with any kind of fundamental reason why. But it's important to understand that there's the mass from this law and the mass from inertia, and they turn out to be the same, although there's no reason in classical mechanics why that should be true. It's a feature of the universe that's not explained by the theory, but is just included in it. Universal gravitation is called an inverse square law because it depends on the square of the distance, that F sub g, F sub big G, is proportional to 1 over r squared. It depends on the inverse of the square of the distance. Doubling the distance between two objects reduces their gravitation by a factor of 4. Also notice that because of that, since r squared never is 1 over r squared is never 0, the force of gravity is effectively infinite in this model. Everything everywhere pulls on everything else. But 1 over r squared is a pretty fast decline, and so generally we can ignore other objects. All right, that generally there'll be 1 or 2 objects in a vicinity that are important, and the others will not exert significant gravitation. All right, let's do some implications of these. So we have planet X with a mass 2m and planet Y with a force over the mass 1m, and we want to know the force of planet Y on X. So planet Y is going to pull planet X this way, and how does its force compare to the magnitude of X pulling on Y? This is almost a trick question. It has nothing to do with the fact that it's gravity. It has to do with the fact that they're Newton's third pairs. Right? The force of X on Y and the force of Y on X will always be equal in magnitude, no matter what kind of force they are. The gravitational force between these two asteroids is 1 million newtons. Dun, dun, dun. Doesn't matter. What will the force be if the distance between the asteroids is doubled? Well, again, remembering that Fg is proportional to 1 over r squared, doubling the distance, making the bottom twice as large, means we get 1/4 the force. So it would have to be this one. All right, the International Space Station orbits at a height of 408 kilometers. That's the distance above the Earth, so the distance from the center of the Earth is a little bit larger. Let's keep that in mind. That's an important reference. We have the Earth, which has some radius, and here's the space station, and we're told the height of the space station above the Earth. So the actual distance between the r that we need for our equation is the sum of the radius plus the extra height. One of the simple, easy ways to make a mistake on this exam is to not pay attention to when they're talking about distance between centers or height above a surface. If you're height above a surface, you have to add the radius of the object back in to get the total distance from the center. All right, given that information, let's find the acceleration of freefall on the International Space Station. Let the mass of the Earth be m, mass of the ISS be lowercase m. All right, from Newton's second law, we have that F net equals ma. So ma is the gravitational force, gmm over r squared. But if we had the space station on the Earth, which I do not recommend because it's not structurally meant to be on the Earth, but if you were to bring it to the Earth, it would have been the same kind of thing, but the acceleration would have been g. The gravitational force would be m times g. And that would be gmm over re squared. And then since a lot of these things are constant, a usual technique is let's take the ratio. So let's take the ma over mg, and then take what they're equal to over here. So ma over mg, what they're equal to over here. Why do we do that? Because a lot of things go out. The m's cancel. These m's cancel. The original m's cancel. And maybe most importantly, the constant g, whose value we don't know yet, also cancels out. And when everything is said and done, the ratio of a to g is the radius of the Earth squared over the radius of the orbit squared, which we can say is just the ratio of orbits squared. We put that in, and we find that a is going to be this number squared times 9.8, or 8.7 meters per second squared. Let's not go too fast past that. The Earth pulls roughly 89% as strong on astronauts in orbit as it does at the surface. Astronauts are not weightless because there's no gravity in space, or they're beyond the reach of Earth's gravity. Phrases that you often hear on the news, for instance, when people are talking about these things. Astronauts appear weightless because they're in continual free fall. We talked about that earlier. All right, that they appear to be weightless because everything around them is also falling with them, and of course they do it for a very long time, and we don't think of that as falling. But it's not because there's no gravity in space. Getting the value of g is actually tricky, and it took more than a century for scientists to discover anything resembling the current accepted value. We could use the moon's known period and distance to compute its acceleration, and then use that and the result above to compute g, but then we would need to know the mass of the Earth, which was not easy to ascertain either, in fact was not known until we knew the value of g. How do you measure the value of g? Well, one way was by a guy named Henry Cavendish, and he took two large spheres on a thin rod and attached them to a relatively thin but strong wire, and then took another large sphere nearby. So imagine not in the line of the orbit, but sort of out of the page nearby, and caused this one to be attracted more than that one, which caused a twist in the wire. And then he would figure out how much the wire twisted and could figure out g, since he knew the mass of the two spheres and their separation. This was ludicrously hard, especially in 1780 or so. It's actually really hard today. There's a video online about a guy who's like, I'm going to do this in my physics class, and spends about 30 minutes, much of which is at high speed, at time lapse, so you can see like hours pass. He spends the whole day doing it and can still see when he walks on the floor, and it creates a greater deflection than the two spheres. So this is a really hard experiment. It's not one we're going to do in class. But it's been done carefully by people who have more time and enthusiasm than we do, and find that the current best value for g is 6.67 times 10 to the minus 11 Newton meter square per kilogram square. These units are bizarre and do not try and put a lot of meaning in here. They're just what we need, that when we multiply by an m and then another m, so we get kilograms times kilograms on top, and we divide by a distance squared, we want these things to cancel out those things. So that's all that, those are where those come from. They're completely driven by practicality. The number is relatively, in fact, tiny, and we'll see that in a second. Compute the force in newtons between two 65 kilogram persons separated by 2 meters, pretending each person is a point particle, because we don't have calculus to do the other bit. All right, it really is just plug and chug here. G m1 m2 over r square. So f sub g is this very small number, Newton's meter square per kilogram square. Times 65 kilograms times 65 kilograms over 2 meters all squared. Turns out to be 7 times 10 to the minus 8 newtons, or 70 micronewtons. No, sorry, 70 nanonewtons, about 0.7 micronewtons. The force is extraordinarily minuscule. It's tiny for ordinary objects near on ordinary distances. That kind of force is so much less than air currents if you were to do those. That's why the guy had to use like these really huge ion spheres and so on, even to do the Cavendish experiment. Because of that, gravitational forces are generally only significant when at least one mass is truly astronomical, planetary, or larger. We tend to only worry about universal gravitation when we have objects that are supermassive, that are in the 10 to the 24 or larger kilograms.